Chapter 4, Fire Streams. Our objectives for this chapter: define a fire stream, recognize the common sizes of smoothbore nozzles used in the fire service, explain some of the factors that affect the reach of a fire stream, explain the difference between the horizontal reach and the vertical reach of a solid stream. Determine the approximate horizontal reach of various streams using the horizontal reach formula. Determine the approximate vertical reach of various streams using the vertical reach formula. Understanding the various factors affecting the penetration of a fire stream into a building. Work problems to determine the penetration of a stream into a building. Work problems using the formula c² equals a² plus b². Describe the difference between a direct attack and an indirect on a fire. Explain the differences among automatic nozzle, fixed gallonage nozzles, selectable gallon nozzles, and multi-purpose nozzles. Define the velocity flow of water moving in a hose line. Determine the velocity flow when the head is known. Determine the velocity flow when the pressure is known. Compare the velocity flow in a hose with the velocity flow at the nozzle tip. Solve problems to determine the velocity flow from the nozzle tip when the velocity flow in the hose is known. Determine the nozzle reaction from a solid stream nozzle. Determine momentary nozzle reaction from a solid stream nozzle. Solve a problem to determine the nozzle reach on fog nozzles. Compare the nozzle reaction on various nozzle tips. Describe some of the safety factors that should be followed when working streams from ladders and elevated master stream appliances. The basic foundation of the fire department operations has always been, and probably always will be, the effective use of fire streams in extinguishment operations. The best chance we've seen in the fire service has been the adoption of large hoses for firefighting. We now use an 1 3/4 line for residential fire instead of an 1.5 lines. We can flow much more water than ever before. With the large lines, we can get more gallons per minute with less pressure. As well, with the use of LDH, which is your large diameter hose, it has been said that we can move fire hydrants from a static position to a mobile position in front of the fire. Essentially, we are getting the water closer to the fire, thus reducing our friction loss and allowing for greater gallons and pressures to be delivered. Because of low friction loss in LDH, supply lines can extend over long distances. For example, moving 500 gallons per minute through a 5-inch hose only resulted in a friction loss of about 2 pounds per square inch per 100 feet. The friction loss in 1,000 feet of 5-inch hose moving 500 gallons per minute of water is only 20 psi. A 1,500 gallon per minute pumper at a strong hydrant could easily move 1,500 gallons per minute over 1,000 feet. The old way of using 2.5-inch hoses for supply lines would require a lot more pressure to supply the same gallons per minute. Good tactics on the fire scene involve putting your people and equipment in the right places to extinguish the fire as quickly as possible. This is accomplished with the use of fire streams. A fire stream is defined as a stream of water from the time it leaves a nozzle until it reaches the point of intended use or until it reaches its projection limit, whichever occurs first. As the stream leaves the nozzle, it is affected by the discharge pressure, the nozzle design, and the nozzle adjustment. There is a wide variety of nozzles and nozzle types that can be used in firefighting. but all of them provide two basic types of stream: a solid stream and a non-solid stream. Solid streams are produced by smoothbore nozzles or some fog nozzles adjusted for solid stream application. Good solid streams have the ability to reach long distances and can penetrate areas and material that cannot be reached with non-solid streams. Smoothbore nozzles range in sizes from a 1/2 inch tip to 3 inches. Booster lines usually have a 1/2 inch to 3/4 inch tip. Large handheld lines usually will have the tip sizes of a 7/8 inch to 1 1/4 inch tip. Any hand line with a smoothbore tip is supplied at a pressure of 50 psi at the nozzle. And you're going to need to remember that for future calculations, guys. Smoothbore tips must have a pressure minimum of 50 psi at the nozzle. 350 gallons per minute is about the most you would flow on any hand line. Any discharges over 350 gallons per minute is no longer considered a hand line, but a master stream. Master stream appliances usually flow over 350 gallons per minute. The large smoothbore tips are used on these, and their discharge pressure is 80 psi at the appliance. So again, here's another constant that you will need to remember for your calculations. The tip size on a smoothbore appliance range from 1 1/4 inch to 3 inches, usually in 1/4 inch increments. Reach is a measurement of the distance that a fire stream can be effectively thrown from a nozzle and still be classified as a good stream. There are a number of factors that affect the reach of a fire stream. One of these is wind. Obviously, the more wind there is, the more it's going to affect the stream and break up the pattern. Even a moderate breeze may reduce the effective range of a solid stream anywhere between 15 and 20%. As water leaves the tip, it is acted upon by gravity, which makes it curve toward the ground. Another factor that affects the fire stream is the nozzle pressure. A good example of this would be your average water hose at your home. You turn the water hose on, and then the water comes cascading out. However, if you shrink the opening of the water hose with your thumb, you get a solid stream that goes much farther, and that is directly in proportion to the effect of the buildup in pressure in the hose. Most departments have standardized the pressure depending on whether it is a hand line, which is 50 psi, or a master stream, which is 80 psi. Remember, these pressures are for smooth bore nozzles. Solid streams may be used at ground level or projected into the upper floors of a building. These streams are referred to as horizontal streams and vertical streams. Horizontal reach. A horizontal solid stream is one with an angle of discharge of 45 degrees or less. Theoretically, a solid stream has its greatest horizontal reach at 45 degrees. However, earlier studies have found that 32-degree angles give the greatest horizontal reach. The following are some general rules for estimating the horizontal reach. The approximate reach is for an 1 3/4 inch line times the nozzle pressure at 20 psi. 1 1/2 inch times the nozzle pressure at 50 psi. 1.25 times the nozzle pressure at 70 psi and equal to the nozzle pressure at 100 psi. Okay, gang, so here's our first formula. There are two formulas for finding the horizontal reach, one of which follows this. S equals the square root of HF times P, where S equals distance, HF equals horizontal factors, and P equals nozzle pressure. For these problems, you will need to refer to table 4.1 on page 80 in the text. So let's go ahead and try to work a problem. What is the approximate horizontal reach of an 1.25 inch tip with the discharge pressure is 40 psi? So distance is S is what we're solving for. So S equals the square root of our horizontal factor times pressure. Horizontal factor we will get off of page 80 and 81. So we used an 1.25 inch tip. The horizontal factor is considered to be 92. I do not expect you to remember the horizontal factors. Now, our pressure is 40 psi. So to figure out our horizontal reach, we first need to multiply 92 times 40. So 92 times 40 equals 3,680. So in order to get our distance, we need to get this square root of 3,680. And that's simply a number times itself is basically a square root. So go find the square root button on that magical calculator that I'm sure all of you guys have. And then the answer comes out to be 60.7 feet. And here's the step-by-step written out for you again. And just a special note here that a horizontal factor is a 5/8 inch tip with a factor of 62. And there is a factor increase of 6 for each 1/8 of an inch in tip size. So basically, you can start with remembering, if you wanted to, that a 5/8 inch tip has a horizontal factor of 62, and for every eighth it goes up, it's going to increase by 6. That way you don't have to remember the whole chart. The second formula you can use for finding the horizontal reach is 1/2 P plus 26, where S is going to be our distance and P is our nozzle pressure. The formula is for the tip size of a 3/4 inch and larger with the nozzle pressure over 30 psi. For tips larger than 3/4 inch, add 5 to the 26, and for each 1/8 inch increase in tip size. I believe personally that the first formula is far more easy to use. Okay, so let's go ahead and try working this problem. We know that, let's see here, what is the approximate horizontal reach of a 1 1/8 inch tip where the discharge pressure is 50? So our reach is always S, and that's 1/2 the pressure, or 1/2 times the pressure. We know the pressure is going to be 50, so that can easily be written as 50 over 2, because it's 1/2 times 50 over 1, multiply across, and that gets 50 over 2. And then, of course, 50 over 2 is going to get reduced to 25. So S equals 25 plus 26 plus 15. And that 15 here comes from this section, where when you're more than 3/4 inch, you have to add that 15 to it. So let's see here, 25 plus 26 plus 15. That's going to give you about 66. 25 plus 26 plus 15. Yep, that is correct. That is 66 feet. Okay, so we've looked about going horizontally. Now let's look about going up with vertical. A vertical stream is one in which the angle of discharge is greater than 45 degrees. Vertical streams are used to get water into a multi-story building from the outside. For a hand line, usually the second floor is the highest floor for which we can get an effective fire stream in from the ground. So our formula is going to be S, which equals our vertical factor times our pressure. So let's use a 1-inch tip and a 40 psi pressure. So S equals the square root, and we know our pressure is going to be 40, and you've got to look up your vertical factor, and that's going to be on page 83. And we said a 1-inch tip, so that's going to be 105. So 105 times 40 is what? 4,200. And then we've got to square it. So 4,200, hit the old magic square root button, and we get 64.8 approximately. And granted, there's a little bit of rounding in there, so I'll catch you a break on the decimals. So if it's over 5, round up. If it's below 5, round down is fine. So our distance is 64.8 feet. And if you haven't already, you need to make sure you get a calculator with a square root button. Just a good old simple calculator with a square root button will suffice. Or break out those handy dandy graphing calculators if you still have those. Master stream appliances on apparatuses or ladder pipes or elevated platforms are used more often than hand lines for projecting streams into the upper floors of buildings. When using master stream for an elevated attack, it is recommended that the apparatus be spotted across the street from the burning building. The formula for determining the vertical reach of a solid hose stream is in S equals our vertical factor times P, where S is distance, and then of course P is pressure. So it begins with a 5/8 inch tip having a factor of 90, and it goes up by 5 for each 1/8 of an inch or larger than a 5/8 inch. So working out our formula here, S equals our vertical factor, and that's off an 1.5 inch tip, which is going to be, can't forget our square root, 125. times our pressure, which is 50. So 125 times 50 equals 6,250. And then our square root of 6,250 equals 79.06 feet. Stream penetration is the penetration of water from a hose stream into a building. The effectiveness of a stream discharging water into a building depends on how much water actually gets to the seat of the fire. In most instances, this requires that the water penetrates some distance into the building. Maximum penetration occurs when the stream enters the building just above the windowsill. Penetration is also greater at lower angles than at higher angles. Attempting any degree of penetration into a building is impractical at angles greater than 75 degrees. And here is a great chart to illustrate this principle. At 30 degrees, here's your reach. At 45 degrees, here is your reach. And then here at 75 degrees. So the more you can minimize this angle right here, the better off you're going to be. So that's why they said if you can shoot it in the window right here at the windowsill or at the base of the opening, that is going to give you the most reach. And hopefully that will get you your fire. However, there are other fire behavior principles in play here, where simply put, if you can bank the water using indirect attack into the room, that water is going to, of course, convert to steam and start extinguishing the fire by absorbing the energy. So that's going to at least help reduce it or knock it down for interior operations. The actual penetration of a stream into a building is the horizontal distance from the outer wall of the building to the point where the water comes to rest inside the building. How far the stream travels after it hits the ceiling depends on the ceiling construction, ceiling height, and some other factors. We can estimate the penetration into the building by using another formula. Of course, we have formulas for everything, hence the goal of this class. Okay guys, don't cringe. Yes, I know, it's another formula. Don't pull your hair out, but it's a pretty simple one. And this goes back to the Pythagorean theorem, or simple right triangles. Simple right triangles are two different sized triangles that have identical angles. In the book, there are two triangles that are similar right angles. There are different sizes, but they have the same angle. So again, what we're looking at here is, oh, I know, our brains are hurting. This is geometry. And that's kind of when you're looking at that whole 90-degree angle. And this is our building. This is our distance from it. This is going to be your stream. So a squared plus b squared will equal s squared. So, given the height of the building and the distance away from it, you can get a pretty good approximation. We can figure out the missing dimensions or angles by comparing the two different triangles. Theoretically, the distance hit by the stream on the ceiling can be determined by comparing two right triangles and putting those figures into a formula. So here's a good example of the two right triangles. We compare these triangles. There are a few things we can assume. We assume that the height of a story is 12 feet and the windowsill is 3 feet above the floor. This means that a ceiling is 9 feet above the windowsill. To determine the unknown side of a right triangle, we must use the following formula. A over B will equal C over D, where A is the height of the ceiling above the windowsill, and B is the distance from the outer wall to the point of contact on the ceiling. To determine the unknown side of a right triangle, we must use the following formula. A over B will equal C over D, where C is the height of the windowsill above the ground level, and D is the distance from the nozzle to the building. So it's going to look something like this. Okay. And let's look at our formula. Some basic algebra rules here. You know, what you do to one side of the equation, you have to do to the other. And this is a proof for those of you that remember your geometry. So let's look at our problem here. So we know that this is going to be on the third story, or floor, shall we say. But that's not going to have a whole lot of effect on A right here, because we know that this point here, coming through the windowsill, so we've got 12 feet high, and again, that's just going to be a constant that we're going to use. And we're going to subtract 3 feet for the window, so we know that A is going to be 9. B, we don't know yet. That's what we're going to have to solve. So we know 9 over B equals C over D. So we know that C is going to be, based off those calculations, 27. And let's just assume that our distance away, so they're going to have to give us that, is going to be 45 feet. So let's plug in our numbers. Alright, so C is 27 over 45, and that equals 9 over B, which our X are unknown, so we're just going to do cross multiplication. So that's going to be 9 times 45 divided by 27 to get B. 9 times 45 divided by 27. So let's get the old calculator rolling again. 9 times 45 is 405. And then we want to divide that by 27. And that gives us an answer of 15. So it is 15 feet in, approximately. So here it is written out for us. A over B equals C over D. A is the height of the ceiling above the windowsill, and it's usually going to be 9. The number B is what we're seeking, and of course C is the height of the windowsill above the ground, and D is the distance from the nozzle to the building. And who said we would never use geometry? I know I'm one. Question. Water is discharged from a nozzle located 60 feet from a building. The water just passed over the windowsill on the 3rd floor. How far in on the ceiling will the stream hit? Okay, so A over B equals C over D. I always recommend, guys, you write your formulas out. That way it gets less confusing. And you just plug in your numbers. And you may want to draw out a picture. Sometimes that helps too. So we know D is the distance away, which is 60 feet. C is going to be our height. And let's see here. We're on the 3rd floor. So using our basic calculation and subtracting the windowsill, that's going to be 27 feet. And that's saying 12 feet per story times 2 stories is 24 feet. And we minus 3 feet. Or no, excuse me, we add 3 feet, not minus 3 feet for the windowsill. And that gives you the 27. So now we have half of our equation. 27 over 60 equals A over B. And A, pretty much, as rule of thumb, is always going to be that 9. And B is what we're looking for. So again, cross multiplication. 9 times 60. And then you're going to divide that by 27 to get our answer. So 9 times 60 equals 540. And then 540 divided by 27 gives us an answer of 20 feet. So B equals 20 feet. Alright, so here's the nice pretty version that's all written out for you to understand. 9 over B equals 27 over 60. So that comes out to be 540 equals 27 times B. Divide the 27. And of course, our answer is 20 feet. The stream will hit the ceiling 20 feet into the building. Okay, so let's look at it a slightly different way now. The nozzle on the ladder is located 63 feet above the ground. So instead of shooting the water from the ground, you're shooting it from the ladder. So that's going to change our height difference variable. The water from the ladder pipe just passes over the windowsill on the 8th floor and hits the ceiling at a point that is 27 feet from the outside wall. So now we're going to kind of change our unknowns a little bit here. So what is the distance from the building to the nozzle tip on the ladder pipe? Again, be careful on this one because the nozzle is already 63 feet off the ground. The same formula is used, but you first need to figure out the vertical distance from the nozzle to the windowsill. Here's a good illustration of how you're going to figure it. So we're looking at our floors. We have 8 floors, right? So that's 84 feet above ground. And again, we're not counting the first floor. So that's 7 floors times 12 is 84 feet. And then you want to subtract 63 from the height of the ladder. So that gives you 21 feet. And then, of course, another 3 feet for the seal. So that gives you a total of 24 feet. So the water just passes over the sill on the 8th floor. So how many feet up is that? Here it's written out. So that's 84 plus 3 for the windowsill. So it's a total of 87 feet up. The nozzle is already 63 feet up. So you just subtract 87 minus 63. And again, that's another way to get there. And that gives you 24. So now we apply our formula. A over B equals C over D. And this time we've already got the A or B side figured out. So that's 9 over 27 equals 24 over D. So now all you have to do again is cross multiply. So 9 over 27 and 24 over our unknown. So 24 times 27 divided by 9. Will give us our answer. So 24 times 27 equals 648, and then you divide that by 9, and that gives us an answer of, and they are right on the slide, 72 feet. Okay, our next formula, c squared equals a squared plus b squared. When working with a right triangle, if we know the two sides, we can figure out the third using the above formula. This formula can be written in several ways depending on what you are trying to solve. With the formula written as it is at the top, try to solve for c. Will mean that the formula will look like this. C equals a squared plus b squared. And this goes back to some basic algebra concepts of what you do to one side of the equation, you have to do to the other. So we're trying to get rid of our exponents here. Let's erase that. So c squared equals a squared plus b squared. All right, and the square root essentially is something times itself. So we know if you take the square root of c and the square root of these, you will get c equals the square root of a squared plus b squared. So now we just need to figure out what a and b are. Some other ways to write the formula can be a squared plus b squared equals c squared. Again, solve for b. All you have to do is change it up a little bit in terms of what you do to one side of the equation, you have to do to the other. So if we want to solve for b, we know that we have a squared plus b squared equals c squared, and we want to get b by itself. So all we have to do is subtract a squared from this side and a squared from this side. So now when we subtract the a squared here, that cancels out. So that leaves you b squared, which equals c squared minus a squared. And then we just do our square roots of each, and that gives you your b equals c minus a. Again, that's your square root. And the c is the same way. Again, you're just moving them from one side of the equation to the other, either by addition, multiplication, or division or subtraction. But in this case, it's all just subtraction. All right, so the biggest problem here with this problem is putting in our numbers in the right spot, because they give me all the information. So here's a real world problem. A nozzle tip is located 45 feet from a building discharge the water through the window on the 3rd floor. The water just passed over the windowsill. What is the length of the stream from the nozzle tip to where it passes over the windowsill? So we know that it's the 3rd floor. So that could be 24 plus another 3, 12 for each story. So that's 24 plus another 3 feet for the windowsill. So that is going to give us 27 feet. RA is 45 feet because that's the distance away, square, which equals C square. So all we basically do is 27 times 27, and then 45 times 45, so that's 729 plus 2025, which gives us a total after we add them together of 2,754. And then we get the square root of 2,754, and that gives you 52.48. So kind of put it in terms of a little chart here. C is what we're looking for. B square is the height of the building. A square is the distance away. Again, we figured out B by knowing that it's on the 3rd floor. We have 12 foot per floor. So we times that by 2. That gives us 24 plus another 3 for the windowsill. So that gives us that 27. A they give us right here. That's 45 feet away. And now you just have to do the math. 45 square plus 27 square. We have square root of C here. So after you get those answers, you square root it. And there you go. So let's look at a different type stream finally. A non-solid fire stream. Non-solid streams are used at fires more than solid streams. Non-solid streams are commonly called fog streams, and that's primarily what we use in the fire service course to do interior attacks. The form of the water droplets from the fog nozzle and the fineness of the mist depend on the design of the nozzle and the nozzle pressure. And the idea being that this is somewhat of a broken stream, so you have smaller particulates of water molecules that will absorb more heat and energy quicker due to the surface ratio. So if we have 1 cubic foot piece of ice and 6 square feet would be exposed, if that 1 cubic foot of ice is broken up into 1-inch cubes, we will get 1,728 smaller pieces, or like chips or shaves, whatever you want to call it. Each of these pieces now have 6 square inches exposed to the heat. So for 1 cubic foot broken into 1-inch pieces, we would get 72 square feet of ice exposed, which again is going to absorb the heat, which is the energy, a whole lot quicker and put the fire out. If the ice is broken into smaller pieces, we get 12 times as much exposed. Therefore, it will absorb 12 times more heat than the bigger piece. The same goes for water. If we can get the droplets into smaller pieces, then it will absorb much more heat. This is the reason we use fog patterns when doing a fire attack. And I'm not saying a full fog pattern, it's what we call a tight fog pattern. And that's another class for another day. This is one premise While if you look at ultra high pressure systems, they are far more effective than what we're currently using. And that's some cutting edge technology that's up on the horizon that I think is really going to change the face of firefighting here in the next few years. In a direct attack, the water is discharged directly onto the material that is burning. Direct attacks can be made using either a straight stream or a fog stream as the need dictates. Indirect attacks, not direct, but indirect attacks, water is applied to the heated atmosphere rather than the burning material itself. When it comes to these combination nozzles, and these are nozzles that can change patterns, and truly with the combination nozzles, they're not truly a solid stream, but they're close enough. And there are 4 basic classifications. You have automatic nozzles, fixed gallonage nozzles, and selectable gallonage nozzles, and of course your multi-purpose nozzles. And here's a good picture of a different, several different sizes of automatic nozzles. Automatic nozzles have been referred to as the thinking nozzle, the self-adjusting nozzle, and the constant pressure nozzle. They're also known by. They are designed to maintain a constant pressure regardless of the flow. This is normally nozzle pressure of 100 psi. These nozzles can shave off pressure with a spring, but they cannot build pressure, so the pump operator needs to supply the correct pressure, if not a little more. Fixed gallonage nozzles. Whereas an automatic nozzle is designed to maintain a set pressure, which will deliver your GPMs, a fixed gallonage nozzle is designed to provide the same flow at a specific nozzle pressure regardless of the pattern setting. Basically, it has a selector on there, and that changes the nozzle on how many gallons per minute you want to flow. So for example, with a nozzle rated at a flow of 150 gallons per minute, the nozzle operator can change the pattern from straight stream to a fog stream, whatever the case may be. But the gallons will still remain at 150 GPM. While most fixed gallonage nozzles are designed to operate at 100 psi, there are nozzles designed to give the same gallons per minute with a pressure of 75. These are used for high-rise situations. You have selectable gallonage nozzles. Selectable gallonage nozzles enable the operator to select a discharge that is suitable for the task. This type of nozzle demands that a close coordinated be maintained between the nozzle operator and the pump operator. The pump operator needs to know what the GPM setting is at the nozzle to provide the correct discharge pressure. So the nozzle will not work effectively unless the pump operator knows how many gallons you're flowing. If the pump operator knows how many gallons you're flowing, then they can set the pump at the proper pressure to make sure you get what you need to operate effectively. Multi-purpose nozzles. Multi-purpose nozzles have the unique ability of providing combination fire streams that include a straight and a fog stream at the same time. This capability provides both penetration streams and a protective stream for firefighters advancing a line into an intense fire. Fire officers give considerable thought to fire problems in a community and the number of personnel assigned to a company whenever they think about purchasing of new nozzles. When considering the selection of a nozzle, thought should be also given to the desired flow and to who's going to control the flow. Basically, the more pressure you're going to get at the end of the nozzle, the more gallons you're going to get to a certain point. And the higher pressure you get on that nozzle, the more difficult it's going to be to handle it, because you're going to have pounds of pressure pushing back on you, and that's going to be nozzle reaction. And we'll talk about that formula later. Velocity flow. The velocity flow of water is the speed with which it passes a given point while traveling in a given direction. The velocity of a stream issuing from an opening depends on the discharge pressure, or what is known as the head, of the water causing the flow. Velocity is usually measured in feet per second, but it may be measured in feet per minute, inches. When the velocity flow is given in 1 unit of measurement, it can readily be converted to another unit. Feet per second can be converted to feet per minute by multiplying it by 60. Feet per second can be converted to inches by a second multiplication by 12. When the velocity flow is given in 1 unit of measurement, it can readily be converted to another unit. Feet per second can be converted to inches per minute by multiplying 60 times 12, which gives you 720. There are several other ways to convert these by dividing or multiplying by 60 and 12. Just whatever floats your boat. Two formulas are used for determining velocity when the head is known. And again, the head is going to be the pressure coming out at the end of the nozzle. So velocity equals 8 times the square root of h. So V equals 8 times the square root of h. When the pressure is known, you're going to use the following formula. Velocity equals 12.14 times the square root of discharge pressure. So let's say your discharge pressure was 50, and that's the pressure to a smoothbore. So the square root of 50 is 7.49, and we're going to multiply that times 12.14. 12.14 times 7.49, and that would give you a discharge pressure, or excuse me, a velocity of, say 91. All right, so here's another one. What is the velocity flow of the water issuing from a hole in the side of a tank if the hole is located 85 feet below the surface of the water? So velocity, again, equals 8 times the square root of h, and h is going to be 85, what they give us. So the square root of 85 times 8. So the square root of 85 is going to be, round numbers, 9.21. Then again, we're multiplying that by 8. And that's how you come up with the answer of 73.76 feet per second. So our formula for this one is 12.14, and that's always going to be the same for this particular setup. So velocity equals 12.14 times the square root of nozzle pressure, which is 50. So the square root of 50 is going to be, what, 7.07, and then 7.07 times 12.14. Get out the calculator here, and that equals about 85.83. The following formulas for determining the velocity when the pressure is known. What is the velocity flow from the tip? And this is what we worked out. It's just all written out for us. Velocity is 12.14 times pressure. And they got 85.84. So, again, just depends on, your decimal points. And I'm not going to gig anybody on that. You get a little leeway. Alright, so now on to nozzle reaction, which I mentioned earlier. Nozzle reaction is a very real reaction that happens as water leaves the nozzle. So to put it in perspective, it's kind of like the amount of force coming out of the bottom of a rocket. And that force pushes that rocket up in the air. But instead of being an actual rocket, it looks like a nozzle and a fire hose, and a firefighter is holding it. So the force of that water coming out is going to be pushing against the firefighter. So the amount of this force is based upon the Newton's third law of motion. For every action, there is an equal and opposite reaction. Great, so not only do we have geometry in this chapter, but we also have, of course, physics and algebra. Some tests were conducted to find a formula for determining the nozzle reaction. So to determine the reaction from a smooth bore nozzle, remember we have two types, use the following formula. Nozzle reaction equals 1.57 times the nozzle diameter square times P. D is the nozzle diameter and P is the nozzle pressure. So the question, what is being discharged from an 1.25 inch nozzle tip at a pressure of 50 psi? What is the nozzle reaction? So we take 1.57 times our diameter square, which is our tip. Diameter is the tip, so that's 1.25. As seen here is 1.25. 1.25 times 1.25, and then you multiply that by 50, and you get 122.66 pounds of pressure that is going to be pushing back on the firefighter. So the question is, can you handle that much pressure? Now our nozzle reaction excuse me, on a fog nozzle is a little bit different. Now since this is a broken stream, it's not a solid stream, the formula is going to be a little different and the nozzle reaction is not going to be as bad. Now in order to figure that, nozzle reaction is 0.0505 times the gallons per minute times the square root of pressure. When firefighters are working off a ladder, it is particularly important that the ladder be secured, as well as that the firefighter be secured to the ladder. The nozzle reaction can easily push someone or something, and that can create a dangerous situation. So here's a good illustration of that nozzle reaction. You don't want to be the firefighter on top, holding that nozzle, spraying into a window against the windowsill in the building, and then getting pushed off the building and come like the special effects there again, crashing down. So let's look at now the nozzle reaction on elevated mass stream appliances. The nozzle reaction of large tip streams at higher pressure is quite high. Particular care should be taken to ensure that the stream works from the ladder pipe are shut down slowly, because if not, then you have that water hammer that we talked about earlier that can cause damage to, of course, the fire hose, the coupling, the pump, and the municipal water system as a whole. The sudden stoppage of water with its resulting shock is called that water hammer. Suddenly closing off a nozzle results in a shock wave that travels from the nozzle to the source. This reaction can be prevented by closing the nozzle slowly. Can't stress that enough. So water hammers can be prevented or at least minimized by partially shutting down the nozzle immediately and then slowly closing it until it completely is off. A partial shutdown releases most of the nozzle reaction and avoids the stress that would otherwise be placed on members. Okay, gang, so we had a lot to digest in math in this chapter. So go ahead and start cracking on your math problems. And if you have any questions, remember, you can always call me in the office at 706-357-0162, or you can email me at aroberts@athenstech.edu, or feel free to look in Blackboard Collaborate and see when the meeting time is if you want some live one-on-one interaction. But if you can't make those times, again, just give me a holler. We'll set something up, and we'll get you straightened out. Until then, be safe and have a good day.